Section 1.3, Closed Sets. Definition 1.14. The subset A of a topological space X is closed if its complement X minus A is open. You see that in the picture up here, that if you have this big rectangle set X and a set A inside, that set A is closed if its complement, which I tried to shade, is an open set. Okay? So being closed does not necessarily mean you're not open. You could be both, or you could be neither, or you could be just one or the other. Right? It doesn't mean that. It means that the complement is open. All right, we also have theorem 1.9. Let X be a set and B a basis for a topology on X. Then a subset U of X is open in the topology generated by the basis B, if and only if, for every point X in U, there exists some basis element B sub X, such that B sub X contains the point X and is contained in U. All right. So this is similar to theorem 1.4 earlier, where it said that if a set is open, if you can always find some neighborhood of every point inside of it, which is contained in that set. This theorem is saying that we can't just find any neighborhood, just any open set in the topology. We can find a special open set belonging to a basis. Okay, so it's a stronger statement, which will come in handy sometimes. All right. So let's take a look at exercise 1.27. The infinite comb C, which is pictured at the right here, is the subset of the plane defined by, well, it's the set of all points x0 with x coordinate between 0 and 1. So that's this closed horizontal interval here. Union with all the points of this form, where the x coordinate is going to be some power of 1/2, and the y coordinate is going to be everything between 0 and 1. Okay, so we're getting all these vertical intervals at an x coordinate of 1, 1/2, 1/4, 1/8, 1/16, 1/32, and so on. And there's going to be a bunch more here that I haven't drawn that will march towards 0, and towards an x coordinate of 0, but never quite get there. All right. So in part A here, we want to show that this infinite comb, strange as it may look, is not closed in the standard topology on R2. All right. Well, according to the definition, to show it's not closed, we must, to show that it's not closed in the standard topology, we must show that its complement, R2 minus C, is not open. Right? Okay, well, theorem 1.9 tells us what it means to be open. So by theorem 1.9, well, to show it's not open, it suffices to find some point xy in R2 minus C in this set, such that no basis element containing that point is contained in this set R2 minus C. Okay. Then theorem 1.9 would say, well, okay, well then the set can't be open. So we got to pick a point and a basis. How about we choose the point 0, 1, and the basis consisting of all open rectangles in R2. Okay, we could choose open balls instead if we wanted to, but this will work just fine. All right, well, given any open rectangle A to B times C to D, containing this point 0, 1, which, by the way, is the point right up here, right? Any other point on that sort of vertical interval would do, except for maybe the origin itself, but we'll use this one. So we have some little open rectangle containing that point. In particular, the interval from A to B contains 0, right? And so that interval also contains some positive numbers. All right? In particular, there is some natural number n such that 1 over 2 to the n is less than b. Okay, so because b has to be positive, we can take a high enough power of 1/2 so that will be less than that positive number b. Well then, we see that this point 1 over 2 to the n, comma 1, which is just a little bit to the right of our original point, is contained in, well, the open rectangle and in C, right? So, what does that say? Well, it says that the open rectangle is not a subset of R2 minus C. Okay. Why? Well, it overlaps with C, right? There's a point that's in this and in C, okay? So there's no way that this could be entirely contained in the complement of C. All right, so that does it. We've shown that the complement's not open. Therefore, the original set, C, the infinite comb, is not closed in the standard topology in R2. In part B, we're going to continue looking at the infinite comb, but we're going to switch topologies. Now we're going to prove that this actually is closed in the vertical interval topology in R2. Okay? So remember, when you change topologies, you're changing what the open sets are on R2. So you're changing what the closed sets are as well. All right. So I've written this one out already. To show that C is closed, we want to show that its complement R2 minus C is open. And we're going to do that by showing that it's the union of a bunch of open sets in this vertical interval topology. Okay. In fact, that it's the union of a bunch of vertical intervals. And they're going to be of 4 different types. And the reason is, what does the complement in the plane of this infinite cone look like? Well, we need to sort of fill in everything to the left of it, everything to the right. And so we'll have a bunch of sort of infinite vertical intervals to do that. And then we need to take the union of all those with a bunch of sort of vertical rays pointing downward from the spine of the comb here all the way down to negative infinity. And then we have to fill in the space in between the teeth of the comb and everything above them. And then finally, the last thing is we need to fill in these sort of vertical rays above the teeth of the comb themselves. Okay, so you do those 4 things. And all right, well, technically the basis of this vertical interval topology was just the finite vertical intervals, like x times interval from A to B. Okay, but you can get these sort of unbounded vertical intervals by just taking a union of infinitely many of those things. For example, to get x times r, you do x times negative 1 to 1, union x times negative 2 to 2, union x times negative 3 to 3, and so on. And you just sort of keep expanding the thing. And the union of all of those will give you this entire unbounded vertical interval. And since it's a union of base elements, it has to be open. Okay, so R2 minus C is open because it's going to be a union of all these different types of open sets. To get the left and the right side of the comb, we'll take these vertical intervals for x negative and x greater than 1. And then to get the region below the comb, we'll take x times negative infinity to 0 for x coordinates between 0 and 1 inclusive. And then to fill in the space between the teeth and everything above those spaces, we will take x times the interval from 0 to infinity for x's between 0 and 1, but not equal to the x values where these teeth occur, powers of 1/2. And finally, to fill in the vertical intervals above the teeth themselves, we'll take the interval from 1 to infinity for x coordinates which are powers of 1/2. All right, and that finishes the proof.